Today, we have with us Dr. Josh Mutus from Rigetti Computing. He's going to give us a behind-the-scenes introduction on Rigetti's quantum processors, including their cleanroom facilities and hardware assembly. Josh is the Director of Quantum Materials at Rigetti Computing, and he has a PhD in physics from the University of Alberta and an undergraduate degree from the University of Windsor. And before joining Rigetti, he worked in Google as a quantum electronics engineer. And prior to that, he did his postdoc work at UC Santa Barbara, and we're very excited to welcome him to the program. Over to you, Josh. Thank you for joining us today.
Thank you for the invitation. We're excited to do this. This is going to be a bit of a whirlwind tour through superconducting quantum processors. The goal here is to I won't have enough time to get into like super detailed stuff, but happy to answer questions. I can join the Discord as well if we want to answer questions asynchronously later. But kind of give more of an overview of what superconducting quantum computer looks like, what's entails in there, and maybe focus on the pretty pictures and the like strategy towards scaling more than getting into the details of like how the 2-qubit gates work and stuff. But I can describe that a bit later. So first of all, who are Rigetti Quantum Computing? We are what we call a full stack quantum computing company based in the Bay Area. We have 2 offices, one in Berkeley, that is shown here, where we have the majority of our engineering teams, hardware engineering teams, and a bunch of fridges where we test qubits on a weekly basis. And then in Fremont, California, we have our fab where we do basically all of the fabrication of our quantum processing units, the QPUs, the actual superconducting quantum chips. You can see sort of a photograph here. We've been around for more than 10 years now. We're a publicly traded company. We have systems that you can buy. Like we kind of target the research R&D market, so universities, national labs, that sort of thing. And we have systems that you can run quantum algorithms on today. We've deployed systems at national labs in the US and even in the UK at the NQCC. We have a office there at the National Quantum Computing Center near Oxford. So first of all, I think a lot of these talks, people are wondering, like, how do I get into quantum computing? Who works at a quantum computing company? Do I have to get a PhD in physics? Do I have to work in a superconducting qubit group to go to grad school to do that? And the answer is actually increasingly no. We have a fair bit of functional diversity at a company like Rigetti, where we need experts across the stack to make things work. So we do have quantum engineers, people that have been working in physics their entire career, characterizing qubits, doing quantum system modeling, that sort of thing, condensed matter physics. And then we have fabrication experts, people from the semiconductor industry primarily, or semiconductor with backgrounds in doing fabrication, e-beam lithography, physical vapor deposition, different coating techniques. And then we have people working in pretty conventional microwave RF electronics, and then also mechanical design. So like I said before, we're full stack, which means we design or build like every part of the quantum computer, from the chips all the way up through the electronics. And I'm sure you can imagine, there's a huge number of specializations that go into that. And so we need experts from all the way across the stack, including the software. So like computer science, software engineering, physics, we have a whole team of folks that are basically making first-party software for our engineers to use to handle the complexity of building larger and larger, more complicated systems. And I'll start at the bottom. My little visual tool here will start at the bottom of the stack. So first I showed a photograph of what our qubits look like on the big golden, so if we start here, this is what we call the puck. This is a printed circuit board that we put at the bottom of our fridge. This little chip here is our superconducting qubit chip. If we zoom in on that in a scanning electron microscope, we can see the important parts of our qubits. So these little Mickey Mouse ears define the capacitor of our superconducting qubits. And you can think of a superconducting qubit as a resonator, essentially. So like it's a slightly nonlinear resonator. So it's just like a pendulum, the ball swinging on a pendulum, or a resonant cavity for like an organ pipe or something like that. But we have, instead of converting from the energy from potential energy to kinetic energy, we're converting energy from resonating between charging a capacitor to current going through an inductance. And the thing that it's just an LC circuit. So folks from an electrical engineering background, it's just an LC oscillator with a resonant frequency around 5 gigahertz. And I'll talk a bit about what makes it quantum. But when you look at the pieces from a bird's eye view, you see this big capacitor, this big piece of metal, and the capacitance is just the capacitance between the two sides of it and the ground that defines the C. And then the L is actually this very, very special component we call a Josephson junction. So it's defined right here. So this is actually a fairly large scale bar. This is 200 microns. As we zoom in and zoom in and zoom in, you start to see this little cross show up here. And if you take a cross section across this cross, you see 2 layers of aluminum with a small layer of aluminum oxide, just a nanometer. And that's essentially the magic component that allows us to make a superconducting qubit. This is a nonlinear inductor, essentially. And so this L and the C define the frequency, it defines the nonlinearity, and it tells us basically what frequency we use these qubits and what operating temperature we can use. Because we want to work in the quantum regime, we want to make sure that there's no black body radiation saturating this oscillator. So we have to put it well below the temperature of this radiation. So we operate at 20 millikelvin. We put them in a dilution refrigerator. The way that we then take these isolated qubits, these isolated LC oscillators, and operate them is we couple them to other elements for either readout or for interactions. So we need to both measure the state of the qubit, but we also have to be able to manipulate it and couple them to neighboring qubits so we can entangle them and make larger and larger quantum systems. To do this, we have to interface them with basically more wires. And this is an optical microscope of a fairly old qubit at this point, but what's kind of neat is that you can see these essentially with your eyes if you were to hold them with your hands. And again, the qubits themselves are these capacitors. So this big island, the capacitance defines this. You can't see the Josephson junctions, it's too small on the scale. But to read them out, we couple another just linear resonator. So just like a guitar string on an organ pipe, you have a resonator that's defined by its electrical length. And the resonant frequency of that is affected by the state of the qubit. So we can use this to kind of gently infer the state of the qubit without totally damping the quantum state. And then to couple the qubits to each other, we can basically just use capacitances. So what's nice about superconducting qubits is that you have a lot of freedom to do essentially like undergrad circuit analysis to define the interactions of your quantum circuit. You can just use like the kind of tools that you'd use in first or second year electric circuits. And that defines like the coupling rates between your circuits. You're not stuck with the atoms that nature has given you to figure out what your coupling rates are, what your interaction strengths are. You have a lot of latitude to do that. But anyway, so we take these qubits, we fabricate them on a chip. I should say that this chip here is a silicon chip. So everything you see here that is kind of like a darker gray is the silicon where the material's been etched away. Everything here that's a lighter gray is niobium. So we start with a planar film of niobium, we etch away and define the structures that you see here. So yes, it's traditionally we've been using fixed coupling to define this capacitance that sort of set our 2-qubit gates, but we've more recently moved to tunable coupling. How does this all look together when you start to assemble a full system? So like I kind of hinted at the beginning of my talk, you take a qubit chip, you put it into some package. We use these like printed circuit board pucks. We have a lot of microwave lines coming out to like address and control the qubits. We put this in what we call a tower. The tower is essentially a magnetic shield and some other kind of sources of isolation. And we put this in a dilution refrigerator, the base temperature of a dilution refrigerator. And a dilution refrigerator is like a set of nesting dolls where each stage has a stage outside of it that is thermally isolating it from higher and higher temperature radiation. So we kind of button this thing up, we put it in the mixing chamber, and then we put like another can around 100 millikelvin, and another can around it that's 800 millikelvin, another can around it that's 4 Kelvin, and 50K, and so on, so that the the qubits themselves are really isolated from the environment. And we have to do the same thing along all the signaling wires. So we have coaxial cables running up and down the fridge. They all have to have a certain amount of attenuation and filtering. There's a lot of detail to the design here, but this is sort of how the systems look. So I kind of showed specifically how we've made systems like a while ago, but what I want to kind of hint at just quickly and more as like a sort of inspirational message of what we're doing. But we can't scale these sort of like small chips that have like perimeter wire bonds. We have to actually make something that we can put hundreds or thousands or tens of thousands of qubits together. And what we need to do this is, or we think we need, what we've decided we need to do here is make a modular system so that we can take chips, we can tile them together, we can entangle qubits across these tiles, and we can prove to ourselves that we can make a system that's kind of like arbitrarily scalable, so we can do larger and larger algorithms. We've been pursuing this for almost the last 10 years now, starting from 2017, and pushing both scaling, so the number of qubits we have, but also really crucially in performance. And the story here is going from these agave type chips to these chips, where now we've been able to get up to like the forefront of the field in terms of 2Q gate fidelity, up past 99%. The way we've done this is we've gone from these kind of planar architectures where you can sort of see what's going on by looking at the chip, where all of the connections come around these perimeters here, you wire bond signals in, to a flip chip architecture where we have a carrier die that has through substrate via. So we drill holes, not with like a physical drill, but with like chemical etches. We drill holes through the carrier chip, and then we can apply signals through this perforated top layer. And this allows us to scale more gracefully, in that we're not like having to put a wire at the perimeter of a rectangle to get a signal inside. We can do this directly, and we can have like a similar pin pattern on our PCB, and then just kind of like tile chips laterally to get there. And so it's taken a lot of effort, a lot of R&D time, a lot of engineering hours to get this signal delivery, this vertical signal delivery working. But now we can do it and get kind of like world-class fidelities using a scalable signal delivery. And this also allows us to stack elements of our chip vertically. So instead of just putting everything planar on this die here, like you see here, all of these different elements can now be stacked on different faces of chips. And this is kind of just indicated by this like black and white image here. Not only have we gone to change our signal delivery technique, but we've also changed both the connectivity. So going from like a low connectivity of these like octagons where only the green dots are qubits here and the blue dots are, or the blue bars are the 2 qubit interactions, where we have these octagons and squares connecting them to like a full square lattice. So we've been able to add connectivity to this, but also using what's called a tunable coupler instead of a fixed coupler. So instead of having like a fixed capacitor executing a 2 qubit gate between them, we have tunable couplings, and it just allows us to have a higher 2 qubit gate fidelity, faster 2 qubit gates. And so, yeah, this demarcation point here between static coupling, tunable coupling has really allowed us to go to higher and higher gate fidelities. Moreover, in the last couple of years, we've been trying to extend this further, not just in a single chip, but across multiple chips. And this is work that I'm really proud of that we put out last year, where we can take this tunable coupler, think of it as like a piece of hardware that you use to connect 2 qubit chips. But instead of it being on a single or 2 qubits, instead of it being on a single chip, we can actually have it straddle multiple chips. So we have this coupling element that allows us to couple a qubit here and to a qubit here while crossing multiple different chips. And we wanted to see how high of a fidelity we could get. So we also wanted to kind of stress test this to see if we added multiple chip interfaces. So not just going from 1 qubit chip through a carrier to another qubit chip, but going from 1 qubit chip to a routing chip to a carrier chip to the qubit chip again. So going across like 3 chips across 5 interfaces to see that we can actually operate the tunable coupler, which is this observation or this ascertaining that you can actually get this like G equals 0 coupling condition. So we show here basically that the theory matches prediction, that we can actually operate it as a coupler. But moreover than that, we can actually get basically indistinguishable gate fidelity. So the performance of these couplers that go across chips is the same as the performance as the couplers between chips. So this gives us a lot of confidence that we can now push these technologies to scale to larger and larger system sizes. Moreover than that, I know we're running out of time. I want to make sure I have enough time to answer questions. Moreover than that, we have a lot of efforts, engineering efforts on increasing the manufacturing precision of our devices. So that Josephson junction that I talked about at the beginning, that like 2 nanometers of aluminum oxide between aluminum layers, that's a really hard thing to manufacture precisely. But what we found is that by using a probe station at room temperature, basically just like measuring the resistance at room temperature, putting like 2 little pins on our qubit islands and applying this alternating series of bias pulses. Just these take seconds. This can happen just on a benchtop. We can tune the frequency, the resistance of these junctions and the frequencies of our qubits by as much as 80% and get order of magnitude in tuning precision. So this is something that's helped us in a lot in the last year, and will continue to kind of help us scale the larger systems because we can target the precisions of target the frequencies of these qubits more and more precisely as we do this. And so we're embarking on this really ambitious R&D effort to like prove out this scaling. So taking our Ankaa chips, these 84 qubit chips, and tiling them together in this larger substrate that we call the waffle, so that we can prove out this intermodule coupling, this interchip coupling at larger and larger scale. And in fact, the chip that we have cold now that we're testing is sort of a proof of concept device, this 36 qubit device where we take 4 9 qubit chips. So these are actually photographs of a very similar chip. All of the dots you see are the vias that we're using to apply signals. We take those, we tile it together in a larger carrier, and we have 36 qubits, all with the inner chip like the couplers between them. And this is something that we're going to try to benchmark in the coming months, hopefully to show that we have the same performance across chips as we do within chips, to really prove that we have this like lateral scaling. We have a credible lateral scaling thing. So that's a bit of a whirlwind tour of us and superconducting qubits. I hope they have lots of questions. I put my email here if people want to just reach out sometime. Here's a really cool photograph of like one of our more recent fridges, the Ankaa fridges, where we put a lot of R&D effort, touched a lot of different specializations from mechanical engineers, cryogenics, electrical engineers, fabrication people to like make this very, very cool looking fridge. But yeah, thanks a lot for the opportunity. Look forward to questions.
We have a few that have come in, Josh. So we've got a question from Roman who asks, in what ways are quantum chips different to classical ones?
Yeah, I think the primary difference is the microwave loss. So people make chips that work at RF frequencies all the time, like gigahertz frequencies. But if you have, say, your Intel chip or your ARM chip in your laptop, it's working at 2 gigahertz. But it's also like you're supplying power to it all in this time you're making it oscillate. We want to put an individual photon at 5 gigahertz into our chip, and we want it to last a really, really long time. And any kind of coupling to unwanted materials modes kind of pulls that energy away and decoheres the qubit. So we have to be a lot more careful about the materials that we're using. So it's a really common dielectric in normal integrated circuits is silicon dioxide. We basically can't use that because it's too lossy. It damps away all of our stuff. So you'll see these chips, everything's kind of planar and big. These capacitors you can see with your eye. If we were to be able to use the same materials you can in like conventional VLSI, we could make like parallel plate capacitors with dielectric in them, but we just can't because the materials just don't work either at the quantum level of like single photon excitations or at the temperatures that we're looking at. And the other big difference is we have to use superconductors for all of our metal layers. And there are a few metal layers that are superconductors, like aluminum is a good superconductor, but by and large, we're using a very different material set than a conventional foundry.
Thank you. One more question has come in. So do couplers between chips perform entanglement in approximately the same speed between qubits and different chips compared to qubit chip?
Yeah, it's a great question. Like, so that's essentially what we wanted to measure here, is that we could get the same coupling rates between, so that's the speed that you can do a 2-qubit gate to generate that entanglement is essentially the coupling rate between the 2 qubits. And what we show in this paper is that we can achieve the same coupling rates with the inner chip coupler as we could with the one that's in the chip. And since then, like in our internal stuff, we've been able to push that to even higher coupling rates because the faster you can generate entangle 2 qubits, the better for just a lot of reasons. But by and large, they're basically the same as the ones that are on the chips. That's the goal.
Thank you. So in one of the slides, it was shown that Aspen used an octagon square configuration, but that your Ankaa uses a square-based configuration. Why is that?
More connectivity is better for a number of reasons. So the more neighbors that each qubit is connected to, so it is useful for basically spreading entanglement across a chip more quickly. And the more entangled your quantum system is, the harder it is to simulate. So the more expensive the computation you can do. So if you think of it from simple like random circuit sense or like a quantum supremacy sense, like the Google demonstration a number of years ago, the more that's basically like a horse race between a quantum computer and like a classical HPC. And the higher this bond dimension, so the more entangled your chip is, the harder it is to simulate, which is really good. The other thing is we're looking to basically build everything forward compatible for quantum error correction. And to do quantum error correction, it's a whole kind of like hour talk on its own. We want to do repeated measurements between groups of qubits. And the most well understood error correcting code is called the surface code, and it uses this square lattice of qubits. So it just maps really naturally onto that. And so if you look at the Google Willow result or some of these other results on surface code, they all use a square lattice, and that's kind of where we're pushing.
Thank you. Why did Rigetti choose superconducting qubits and not another modality?
I mean, I guess I can't really speak for the thinking at the time, but I think superconducting qubits offer sort of the best balance of many, many factors. So they're pretty high fidelity. You don't have the world leading fidelity of quantum 2Q gates or 1Q gates, but they're pretty high. They're sort of within spitting distance. But you can also like easily get a lot of them onto a chip. So this is like an 84 qubit chip. So it allows us to get a lot of qubits, so make a large scale system. Of course, maybe not as big as some of these neutral atom systems do. They can use lasers to build a big thing. But then the gates are also really fast, so you can do things like 1Q and 2Q gates and measurement like a factor of 1,000 to a factor of 1,000,000 faster than those systems. So if you're to kind of draw a surface of this like multi-dimensional thing in terms of like fidelity, speed, scalability, and a bunch of other axes, I think superconducting qubits offer a really good compromise between a bunch of these factors where it maybe isn't the world leader in any one of them except for maybe gate speed. And that's why I think it offers like a nice way to make a quantum computer basically.
Thank you. I think we have time for one or two more, so they're coming in now. Is there any reason to have the diameter of the disk being larger as we move upwards?
So basically, inside of these disks all have a can that's not shown that go on top of it. So they fit together like nesting dolls. So each interior doll has to be smaller than the one outside of it. So the diameter of the plate, which is the lid of that can, has to be bigger than the one next beside it. So it's an ascending size. That's a good question. Good observation.
I'm just curious. So what got you into quantum?
So I've always been an experimentalist, although now I'm just kind of like a guy who talks and gives presentations and stuff. But I did my PhD in experimental physics, and the courses that I understood the best, or the physics that I understood the best, was the stuff I could like get my hands on. And at the time, I really just didn't understand what this whole quantum computing thing was about. So I was like, I'm gonna go do a postdoc in a quantum computing group so I can get my hands dirty and actually understand what the heck is going on here, because I just don't get it. And then I found John Martinez's group at UCSB, and they were sort of the ones that were like doing the most stuff and getting their hands dirty the most. They're making their own electronics, they're fabbing their own chips, they're building their own fridges. And I was like, whatever happens here, I'm going to learn a lot. And I did. And that was kind of a really good entryway into the field for like a whole multitude of reasons. I think my advice, the way the field has changed now, is if you want to learn the most about quantum computing, I think doing a PhD is a really good way to do it in a group that's doing kind of hardware. You'll learn the most about what's going on. But if that's not really your passion, but you want to work in quantum computing, just find the part that you're really passionate about, whether that's software or like technical program management or like mechanical design. The field is big enough and specialized enough that we need good people from all disciplines. And if you're really interested in quantum computing, just kind of have a really good resume and really good experience in that like specialization that you're really passionate about.
Thank you. I know we're at time, but if you have time for one more question, we've had
Sure, yeah.
that's come through. And this is around, it's quite an interesting one, but what are the main challenges to building smaller quantum computers? So moving away maybe from the large fridges.
I don't know. One of the main challenges is materials. So the fact that we make our chips and our qubits this big because we can't fabricate a dielectric between them. If we had a dielectric, like you could put some oxide in there that was low loss, we could make our qubits smaller right away. And that would save us a lot of time. But then you actually, the biggest bottleneck is actually in I/O. It's actually getting all the signal lines in and out of the chip. So you have to either figure out ways to like multiplex signals on a chip or to make that I/O even smaller. But those are the two big things. It's materials and I/O are the impediments to getting smaller.
Thank you. And thank you so much for joining us today.
Take care. Thanks, bye.